Okay, so the subject that we will be discussing today, we could not discuss before was is linear regression. Just one minute. So this is basically the first topic under predictive analytics. However, uh, Saptarshi took a course on took a session on logistic regression, which had become the first session for you at least. But here we will be talking about linear regression, where there is a y, which is a function, a linear function of x1, x2, and so on. And we write it like this: y is equal to beta 0 plus beta 1 x1 plus beta 2 x2 plus an error. This error is the estimation error, the whatever I could not predict. So why like that? So let's talk about y as a function of x. Let's say if there is only one value is there, one x variable is there, based on which I can predict y. And here in linear regression, y is continuous. Continuous means it is not categorical, it is a number. It takes any value between a range. So let's say this is my y, and this is where I plot my x, and the scatter plot looks like this. Okay, so this is my scatter plot. It can be a little bit varied also somewhere here and there. More or less like this. Now, if I want to explain this, I will try to explain. I can explain it by this line or by this line or by, let's say, this particular straight line. So which one best explains the data, the relationship between x and y? Which of these three lines?
Third line.
The third one. Why the third one? Why do you say that the third one best explains the relationship between y and x?
Is mostly in the middle of the entire scatter distribution. Sort of feels like it is at the middle.
Yes, and it is also moving in the direction in which the scatter plot is moving. So the slope basically of this particular line is towards the slope of the data, and also it is in the middle as you told. So middle can be defined by, like, say, this one is not in the middle or this one is not in the middle because, and the third one is in the middle is because there is a certain exact, we call this intercept. Exact intercept has to be there and exact slope has to be there. Then only this guy will be go through the middle towards the direction in which the data is moving. So both the intercept and the slope makes this particular line the correct fit. So what I will say is that, and how do I write that thing? How do I write that equation? The equation of this straight line can be written as y is equal to mx plus c, where this intercept is the c, and this tan theta is m. So that means if it is theta, then that tan theta will be basically m by 1 or m. So that's how it is defined. This particular straight line is defined. It's we probably have studied this in our school level maths. So I am right now just writing that c, instead of c I'm writing beta 0, which is also the intercept, and beta 1 is my slope, and x. And if I have more than one x, then x1, x2, x3, like that. Now this, as I just told, so then this particular straight line is defined by basically the m and c, or the beta 0 and beta 1. As long as I can estimate this correct value of beta 0 and beta 1, which gives me the best result, best possible fit, I will be good. So the whole idea of linear regression is to find out this correct value of beta 0 and beta 1, which will create best fit. Now, how do I define fit, best fit? Best fit is defined by the predicted y value and the actual y value. For example, let's say for this particular x, the predicted y value is this one. It's a, if I draw slow, I would say a perpendicular line like this is where the predicted y value comes. And let's say the actual y value is somewhere here, which I have an observation for this particular x, which is here. So this distance parallel to the y-axis, this distance will be my error. Like that, I will calculate for each of the points some error, and I will be taking the best value which will reduce this error, which will minimize this error. So, for example, if I have, let's say in my data set, I have y variables and I have x variables. Let's say x1 variable, first one variable. So this is y1, this is x11, this is y2, x22. Like that, I have, let's say, n number of observation yn, x1n. So then what is my predicted y? This is my actual y. What is my predicted y? My predicted y is beta 0 plus beta 1 x11, beta 0 plus beta 1 x12. This will be x12. Beta 0 plus beta 1 x1n. What will be my error? My error is y actual minus y predicted values, which is y1 minus beta 0 minus beta 1 x11, y1 minus, sorry, y2 minus beta 0 minus beta 1 x12. Like that, if I go ahead, then I get yn minus beta 0 minus beta 1 x1n. Now the problem is some of the errors are positive, some of the errors are negative. For example, this one, if I take the error for this one, and this is the predicted value, this is a negative error because my actual value is below the predicted value. And here the actual value is higher than the predicted value. So they can cancel out if I join them, if I add them up. So that's why what I will do, I will take a square as we used to do generally. So I took a square of that. I got the error square values. And then I got a mean error square value. So mean square error. So what is the mean square error? The mean of these values. So to do a mean, what I have to do, I have to add them up and divide by n. What do I add? I add yi minus beta 0 minus beta 1 x1I, square of that. I varies from 1 to n, and this. And then to take things in the same, to make sure that ya and yp, whatever the dimension is there, we get the same dimension. I take a root. So that's why we call it root mean square error. This is what we try to minimize. So I try to minimize this particular value. Now you see here in this whole calculation, what are known? The number of observations in my data set is known. I can see the observations. I know what are the each of these yi values. So these are known. And I know each of these x1i values. These are also known. So our modeler knows these values. This one, and this one. That is known to a modeler. So I as a modeler will know this let's say yi, x1i, and n. These three values are known to me. But I do not know this beta 0, beta 1. I have chosen something and got some RMS score. If I choose some other beta 0 and beta 1, I will get some other RMS score in the same data set. So I have to choose such a beta 0 and such a beta 1, which will minimize my RMS score. So basically, then I can say this RMSE is basically a function of beta 0 and beta 1. Now, how do I minimize? I do, so when I have an fx, to minimize, I do del f del x has to be 0. We solve this. And we make sure that wherever I'm getting the solution, del f is greater than, smaller than 0. That's where that's where it is maximizes. I will. This has to be greater than 0. That's why it minimizes. So how do I say that? So let's say if this is the curve of fx, if this is the curve of fx, this is the slope. Del f, this basically is the slope. The slope has to be equal to 0 to have a maxima or minima. So to be the top value or the bottom value, let's say the slope, if it is like this, if the slope is like this, then this is the minima, this is the maxima, this point. So even here the slope is 0. This is the minima, even here the slope is 0. But the difference between here and here is, in this case the slope is 0. Before that the slope is negative, and after that the slope is positive. That means the slope from negative by becoming 0, it becomes positive. So the change of slope is in the positive direction. First it remains negative, then becomes 0, and then it becomes positive. So del square f del x squared in case of minima will be positive, greater than 0. But here you see the slope is positive. In this side it is going up. In this side it is going down, negative, and at this point it is 0. So in case of a maxima, generally del f squared del x squared, this value at that point will be negative, because the slope is changing from positive to negative. So that's how we find out the maxima minima. So if I have to now minimize this, so if I have to minimize my RMSE score with respect to beta 0 and beta 1, what will I do? I will do del errors, del RMSE, del beta 0 is equal to 0, and del RMSE, del beta 1 equal to 0. Then this will give me one equation, equation 1. This will give me another equation, some equation, equation 2. There are two equations and two unknowns. Solve it. So this part is solved using linear algebra. I'm not going into that details. So do you know, if I give you, let's say, two equations, 3x plus 4y is equal to 5, and 7x plus minus 8y is equal to minus 10. Can you solve it?
Yes.
If I write 7x plus 4xy z is equal to 5 and minus z is equal to minus 10, can you solve it?
No. No.
Because the moment there are three unknowns, I need three equations. Then only linear algebra will be able to solve it. So that we have done in our school days. So this also applies here, that you have two equations and you have to have two unknowns to solve this particular thing. So that's how we solve it. Now let's say if I have more number of variables, instead of x1, I also have, let's say, x2, and this becomes x21, x22, x to n. Then how does the whole story change? This becomes beta 2 x to 1 plus beta 2 x to 2 plus beta 2 x to n. So here comes beta minus beta 2 x to 1 minus beta 2 x to 2 minus beta 2 x to n. And here comes minus beta 2 x to I. Out of that, my x to I is known. The individual values of x2s are known for each of the i's, that means for first to nth observation. However, beta 2 is not known. That will be getting added. So then this particular thing will be a function of not only beta 0 and beta 1, but also of beta 2. So this will also be a function of beta 2. So if there are three unknowns, then I will have three equations. Equation 3. So in that case, I will have three equations and three unknowns solved. So that's how, if I, now this solution, this linear algebra solution will be done by computer on its own. I am not going to teach you right now how to do linear algebra, but you can do it. Means if you know integration, sorry, differentiation, you can do it. It becomes a little bit cumbersome as a calculation. But if you have enough, I would say, what can I say? If you have enough patience, you can do it on your own. So this is how basically this solution is done. Now, there are some factors that we get this beta 0, beta 1, beta 2, let's say. So there are some things that we have to also think about. Now, I got the best possible beta 0, beta 1, beta 2, and I got the lowest possible value of the RMSE. However, this lowest possible value of the RMSE is dependent on what I have chosen as x1 and x2. Let's say I am trying to predict India's rainfall, and I have taken x1 and x2 as, let's say, how much sleep Donald Trump had yesterday, daily. So daily rainfall versus daily sleep hours of Donald Trump and daily sleep hours of Putin. So will that be a good? So I will get some beta 0, beta 1. Question comes up is that whether that should be taken, whether it's a good thing. Versus, let's say, rainfall's case, I took India's rainfall versus, let's say, India's average heat, or last 1 year ahead, or let's say India's deforestation. All these things I have taken. So two regression models were created. In one model, rainfall was a function of Donald Trump and Putin's sleep. In another place, it was a function of the rainfall, and as rainfall was a function of heat and deforestation and blah, blah, blah. Question is that which model will I go for? How will I know that one model is better than other? So to do that, we believe on that lowest, that RMSE score that I got. I told I minimize RMSE. Minimize RMSE means I also minimize MSE. So in model 1, let's say, I got MSE, some value. So what is the function of MSE? MSE is by n summation by actual minus y predicted square, right? For I is equal to 1 to n. That was my mean square error. So we also use a function called coefficient of determination. This is, or in normal terms, we often call it R square value. This is used as a measurement of whether the model is good or not. What is this R square value? Let's say, if I tell you, if I ask you, let's say I have not given any data, any other thing that I have told you, but I have given you a particular a particular cities, let's say XYZ city. You do not know the city's name. The city's name is has been made. Uh, it has been white labeled, and that name is white labeled, and then you have been given last 20 days or last let's say 365 days rainfall data of a city. It has been given, and it was not told also that which date is which date. Means you have 365 rainfall days, but you don't know exactly whether the data started from January or February or March or April. You do not know that. Just 365 observations you have from any random particular. So this kind of a data I've given to you, which is absolutely means basically you have no other information other than those values. And I have told you that can you predict that what will be the rainfall in this particular city today? What will be your prediction? You have 365 rainfall observations. You do not know which day it is. And I have asked you today's rainfall amount.
Basically, we'll be able to sort of give a median value with a range that it can vary. So basically, a seasonality will come in, which will not be able to.
You do not know which season. You do not know which the data, past data is of which date. I have not given you the data, the date. I have only given you some 365 random rainfall data. Forget about 365. I am giving you some random 200 rainfall data. I have not mentioned any date, any month, any year, nothing. Then what will be that? What will be tomorrow's rainfall? If I ask you to pay. You're not getting it? Okay. Let me help you get it. God of you work in model validation, right?
Yes, sir.
What kind of model validation? What do you validate? Can you give a little bit of example?
So we deal with credit risk models and we validate the performance of these models.
So God, I gave you a data set of 1,000 customers. You do not know anything about the customer's name, customer ID, gender, past history, nothing. You do not know anything about the customer. All you know that whether the person defaulted or not, 1 or 0.
Okay.
And like that, 1,000 observations you have. Now I ask you, a new customer has come up. Even for him, I am not giving you any data. And asking you, what is the prediction that whether this customer will default or not? No data, no other data. Just randomly, I'm asking you that whether this person will default or not. And you have last 1,000 persons data. That will be your prediction.
So based on the data which I have, I try to do a linear regression, and then
What is the linear regression coming in? You do not have any X variable.
okay.
You only have one column in your Excel sheet. There is only one column, which is whether this person has defaulted or not, 1 or 0.
Okay. Okay.
In this case, sir, so you'll have total count of 1 and total count of 0. If the total count of 1, so default is like 60% and the 0 is like 40%, then you will say the probability of your next customer coming in will be defaulting is higher than being a good customer. So generally you get sort of.
I don't want higher, I want exact value.
Okay, so you want prediction for that one customer, which is, I mean, that new customer, based on the data which we have, and we only have zeros and ones. against the customers.
Okay. Okay. So uh, there is a reason we do average. Okay. There's a reason it is called central tendency. The term is central tendency. The central tendency, this term comes up because I told that in the very first class because it is talking about the core information. This is the central information that you have about that variable. Without any other knowledge, that core information is the is your prediction, is your basic prediction about the next observation. Means all I'm trying to say that without any data set, your mean is your best prediction of your data.
So I think, sir, isn't it the same which Sandit said?
No, Sandit told, I can only say that this guy has higher probability. Higher probability is also 51%. Higher probability also 50.00001%. Those are not what you should say. What you should say is 60%.
Sir, can we also calculate the mode over here, sir?
You can come again?
Sir, can we have to calculate the mode, or we should the mean will work, sir?
If I ask you the probability, yes, you will go for mean. If I ask you the means if you consider it as a categorical variable and go for mode, even mode is fine. Then you can take one. But we are in this condition thinking about thinking the variables as a linear variable. So in such kind of cases, let's say forget about the defaulting. Let's say Sandeep was Gaurav was a person in physical education teacher, and he measures height. Let's assume, okay. And I have given him that in class 10, the heights are like this. For the last 20 years, these were our height. Now tell me that the next entry in the class 10, whoever will get admission in class 10, what will be his prediction of height? So in that case, there is no mode anymore, no? So you have to either go with mean or median. In this context, we are going for mean. Fine.
Yes, sir. Fine, sir. Thank you.
Yeah. So if mean is my variable, mean is my prediction. So without any model, what I'm trying to say, without any model, is when you do not, a layman will give mean as a prediction, and a layman will have an error, MSE, of y actual minus y actual's mean, basically square divided by n. This basically, if I do not do the n by n part, if I do not take the mean part, then this is the square error. And this square error, we call it as total sum of square. We also call it as total. This is the total highest possible error that you can do. Because a layman also, a blind person will also suggest that the mean is the prediction. So this is the maximum error that you can do. Now, when you have done a regression, which is your model 1, model 1 has sum of square as ya minus yp square. We call it, okay, not square root, I'm sorry. We call it residual sum of square. Remember in ANOVA we were talking about residual. So residual sum of square, but some people also call it regression sum of square. That means after regression, whatever sum of square whatever error is. So sum of square means sum of square errors. Basically, sum of square means sum of square errors. So that is also called as RSS. So then what percentage of error is still left after the model? That is nothing but RSS by TSS. This is the error which is still left in the model, that percentage. And so how much you can explain, that is called R square, or coefficient of determination, which is 1 minus this RSS by TSS. That means the percentage of error that your model can explain. This particular value is used to compare one model with another. If I have one model with Putin and another model with, let's say, deforestation, while predicting rainfall, I will get the R square values and I will compare the R square values. That which model out of these two models are giving me better R square value. Now, can you tell me what is the lowest possible value of this R square?
0.
0 means when my model is, see, when TSS and RSS are same, that means I have no model. Whatever I am predicting is as bad as being blind. Then my R square will be 0.
When you are subtracting from 1, is it the probability which we are finding, sir, by the like the coefficient?
No,
As
it's not
you
the
mentioned, the lowest
probability.
is
So what is
0.
See, understand this. It's not probability. It is, what is TSS? TSS is the total error that you can do, maximum error that you can do. RSS is the error that you have done. So RSS by TSS
Right,
is the percentage of the maximum error that you have done.
Okay, we are searching for the percentage over here.
Yes. See, I have written
Okay,
percentage
okay,
of errors.
okay, sir. So I missed that point, sir.
Yeah. So 1 minus that percentage is basically percentage of error or percentage of error that your model, so in this case model 1, has explained. Or you can call that, instead of, because percentage of total error is basically percentage of variance. This is a function of variance. You see, this is how the variance is measured, right? Divided by n and then take a square root, you get standard deviation. So percentage of the variance of y that your model has explained. That is R square. R square lowest value you just now told is 0. What is the maximum value of R square?
1.
1. When does that happen?
So if you don't have any error in the model.
When RSS is 0, when the value of RSS is 0, that means when y actual and y predicted are exactly same. Only when these are exactly same, RSS will be 0, right? So when these values are exactly same, that means I am absolutely predicting everything correctly, then only R square value will be 1. So 0 to 1 is the range. We say, many people say, I will not say that. Depending on context, what is the cutoff R square value changes. So for example, in an engineering problem which is highly predictable, which is based on science, R square higher than 0.9 is something that we expect. But in a management problem, or in a human behavior kind of a problem, where it's very unpredictable, R square even 0.3, 0.2 is also considered to be okay. So R square, what R square you will consider at the end of the day, what R square you will say that it's good enough, is depends on, without that model, what is your prediction ability? Without that model, how good you are doing the prediction. That defines what R square is acceptable. But generally, R square is used to compare. If I have model 1 and model 2, then I can say that, okay, the model which has the highest R square is better. Now, okay. So this much you have understood up to this point. If you have any question, please let me know. So what did I do? I tell you till now. I taught you how to estimate the values of beta 0, beta 1, beta 2. And once you got these values of beta 0, beta 1, beta 2, I can calculate the measure of goodness of fit. We call it measure of goodness of fit, means how good my model fits. We also call it measure of a measure. Measure means some metric that measures of goodness of fit. So how good my model fits. That's R square, and that's how it's calculated. And this is the background of that calculation. Up to this point, if you have any question, please let me know. Okay, let's go ahead. Now, tell me quickly. Now, let's say there are two models. In one model, I have predicted rainfall. Y is rainfall. Is, let's say, some beta 0 plus beta 1 into deforestation plus some beta 2 into, let's say, number of rivers nearby. Something I do not know what else impacts rainfall. And that's all, plus error. And another model, this is model number 1. This is model number 2. Another model I have taken the same things, deforestation, rivers, plus I also got beta 3 into hours of routine sleep. I got so exactly the same variables, but along with those two same variables, I also got one extra variable, which is hours of routine sleep, which has no relation, practically no relationship with the rainfall. I got here R square, I call it R1 square, here R2 square. Can you tell me which one is true? R1 square is greater than R2 square, or R1 square will be equal to R2 square, or R1 square will be smaller than R2 square?
First one is true, sir.
Third one will be true.
So
Which square will be better?
anybody going for the second one? Nobody is saying, but how many of you are going for the first one? Can you raise your hand? Okay. And Joyendra, why do you think the first one will be the true? Joyendra?
Because so the value will be much nearer to one, sir, in the first scenario.
And this one will not be because student sleep has no relationship.
Equal.
That's what you're saying?
Yes, sir. Because yes, sir.
Okay. Now, and who is saying that the second one will be true? Third one will be true.
So both of them have all the same variables plus an additional variable. So chances are that the second one will have a better R square. Although routine sleep has no relation, but
Why?
because of the extra
Why
variable.
do you think so? Why
Because
if I add one variable, the R square value increases? Why are you saying that? You see, what is R square value? R square value depends on the error, right? And Y actual minus Y predicted square, this, as long as this drops, the R square value increases. Now, in the first case, Y actual minus Y predicted is beta 0 minus beta 1 x1 minus beta 2 x2. That's all. And in the second case, what I am done, I have done YA minus some beta 0 dashed, new beta 0 because it's a new regression, beta 1 dash x1 plus beta 2 dash x2, sorry, not plus, minus beta 3 dash x3, that square. Now you see, when I estimated this beta 3 in this last line, what are the various possible value that I considered for this beta 3? When I did this regression, I found out a value of beta 3, right? What are the various possible value of beta 3 that I considered when I tried to find beta 3? When I do
0 to
0 to, I didn't get you, 0 to?
0 to it can be anything. So 0 to infinity can be the value.
And why not negative values?
Yes, it can be negative as well.
So I have already considered minus infinite to plus infinite, all the values. And let's say I found 0.0002 as the beta 3's estimate. Let's assume. That means what? That means I actually also considered this and found that this is better than this. If the previous one was better than this, then I would have taken 0 here. That's how optimization works, right? And it considers all other values and checks that at which value the error will be minimized. And it is showing that in this particular value, the error is minimized. That means by this data set, I don't care whether put-in sleep is actually affecting or not, but the data set that you have given, based on that data set, I already checked 0 into put-in sleep while finding out this. So this is a fallacy of R square. R square, so as you keep on adding the number of variables, even if those variables are not has any meaning, R square value will keep on increasing. So R square value increases as K, which is basically number of independent variables, increases. That is a problem with R square. Actually, that is a problem with any addition, square addition. A square plus B square, A square plus B square plus C square will always be higher than A square plus B square, something like that. So even if C's value is very low, it will be higher than that. And that's a problem in this particular situation. In this particular situation, even if this value remains 0, this error square, that whatever you are calculating, will always be higher than this error square, because while optimizing this beta 3, it has already considered whether 0 can be put here. That's how the optimization works. So then how to solve this problem? I'm saying that K increases. If I blindly put Sagato sleep, Putin sleep, Trump sleep, Modiji sleep, if I keep on putting, the R square value will keep on increasing. How to solve this problem? So what I start doing is penalizing the R square score. So I say that, okay, R squared is like this, I understand. 1 minus RSS by TSS, which is in other words 1 minus summation of YA minus Y predicted square divided by YA minus Y dash square. This much I understand. But I will penalize the whole data set using some kind of coefficient. I will use a coefficient to penalize this particular equation that we have drawn. So how will I penalize it? I will say that divide this value with n minus k minus 1, where k is the number of independent variables, and divide this value with n minus 1. So this is my total standard error, basically standard deviation. And this is divide this value with n minus the number of parameters. So just see what I'm exactly doing. 1 minus RSS divided by n minus k minus 1 divided by TSS into n minus 1. In other words, I'm saying 1 minus RSS into TSS divided by, you see what I have, it's done. This n minus 1 will come at the top and n minus 1 minus k will come at the bottom. If I write it carefully, which is also means 1 by k into n minus 1. This is how it comes here. Now you see what I'm trying to say. If k increases means the number of independent variable increases. What happens to 1 minus k by n minus 1? This denominator, what happens to this denominator? If number of independent variable increases, k increases, what happens to this denominator?
This denominator will tends to be less.
This denominator will come down, reduce. So then this coefficient will, the whole coefficient, if denominator comes down, then the whole ratio will go up. And if this ratio goes up, this whole thing goes up, then 1 minus this into this will come down or go up?
Go down. So come down, sir.
Go down. So as k increases, r square goes down. I am penalizing. This is a penalty. But we also know that as k increases, my RSS decreases. I have just shown you in the previous this thing that this error will decrease, and that's why your r square will increase. This is the fallacy of r square that I discussed before. So now basically this penalty and fallacy will start a tug of war with each other. So in one side, by increasing a variable inside your model, you will increase the penalty. In another side, as you increase the variable in the model, the RSS will come down. So you will only include such variables in your model which will reduce RSS that much such that it will be higher than the penalty. Because you know that the moment I include something in the variable list, I will have a penalty. But my benefit will be such, because the benefit will be because of what? Benefits will be because of good explanation. Very high reduction of R square. Putin will not reduce the R square enough. Putin's sleep. But deforestation will reduce the R square enough. So I will, if I have a model and if I have to predict rainfall, I will include deforestation, because now by including deforestation, I will reduce R square enough such that the penalty will be overshooted. So this calculation, this new calculation that I just shown, which is n minus k minus 1 divided by n minus 1, this much is called adjusted R square. We actually check this to test that whether a model is better than or worse than another. We don't check R square. We check adjusted R square to compare one model with another. Okay, so I will go one more. Before I go one more step, I would ask you that whether you have understood these concepts or not.
Sir, any so I mean I now recall, I mean, after Sendit's answer that that I mean each time we add a variable, independent variable, irrespective of its relevance, R square would decrease. Sorry, R square would increase, and that's the reason we don't use this as a measure of I mean checking the model's performance. Adjusted R square is preferred, but then do we have any instance where R square is preferred, or we can use it, or this is just I mean not useful for any purpose?
Yeah. So R square by thumb rule for regression is not useful for any purpose.
Okay.
So but before I come to this conclusion, I have to tell you what is R square. Then I can tell you this adjusted R square thing. Adjusted R square cannot come without the understanding of R square.
Okay.
So historically R square were used, and then statisticians found out that there is a mistake there, there's a fallacy there, and then they give a solution which is adjusted R square.
Okay.
There are all other different kinds of R square that you will find out. For example, logistic regression he has taught you. You can search for pseudo R square. Logistic regression we check using AIC value, right? Did he tell you like that what kind of values talk about the model fit? It's a log likelihood value.
Yes, log likelihood. So we had said AIC. I think.
So from that log likelihood value, different kinds of goodness of fit models can be created, and different statisticians gave different models, different equations. One of those pseudo R square that we call in case of logistic regression. One of very popular pseudo R square is 1 minus log likelihood. Log likelihood is what? The higher it is, the better, right? So log likelihood of the null versus log likelihood of your model. Log likelihood of null is up. Just 1 minute. Let me forgot it. Null will be at the top, I think. No, I think I've done it right. Yes. So this is called McFadden's R square or pseudo R square. Just call it pseudo R square. So your model will give you a log likelihood and a model without any X variable. Like here I find out error without any X variable, which is TSS. Similarly, one can find out in that case log likelihood without any X variable. If you do a regression only with intercept, basically what you do is that your log likelihood is nothing but your prediction is the mean prediction. Means you say that all the betas are 0. Now you predict and you calculate the log likelihood. That is your LL null. And then you got some beta values, and based on that you predicted the log likelihood. That is your LL model. 1 minus that is pseudo R square. So this is something which we use. Here we do not do any adjustment in case of logistic regression. But in case of linear regression, we do all of this. Okay, so before I go ahead, I have to tell you one more story, and then I will stop. So let's say y in a regression you got like this: y is equal to 3x1 plus 4x2. Now the problem is that one can ask you that, sir, you got y is equal to these values 2 plus 3x1 plus 4x2, but these you have got from the sample data. The data that you have received is a sample data. No, it is not the population data. It's not the whole. Let's say if y is equal to the performance of the students in the class, x1 is the number of times they come to the class, their absenteeism, let's say, and x1 is their attendance, percentage of attendance, and X2 is, let's say, their family income. If I consider like that, that as family income increases, their performance in school increases, and as they become more present in the school, their performance in school increases. That's why I do this kind of a regression. Now you can say that, sir, you have not taken all the school children all over the world. You have not taken even all the school children in West Bengal. If you are doing it in West Bengal, you have taken only some school, some sample data. Although the sample is, let's say, 1 lakh, but there are probably crores of students in West Bengal, and you have taken 1 lakh sample. So how can I believe this 3 and 4? Tomorrow, if I get another value, if I take another sample, I will get another value. So what is the proof that this X1 and Y are related? So to test that, to test whether beta 1 is equal to 3 is consistent, or at least beta 1 not equal to 0 is consistent, we can do a t-test. And that will depend on what is your null hypothesis. Let's say if your null hypothesis is beta 1 equal to 0, you are saying that, so sir, you have got like this, I don't believe this number. In actuality, X1 and Y has no relationship. So your alternative hypothesis is this. So this kind of hypothesis testing we do, remember, we do it using t-test, and t-value, if you remember what we did, is x minus mu by standard error. In this case, the mu value, the predicted value is 0, and the x value that I got as an estimate is 3. So basically beta 1's estimate minus 0, whatever I wanted to predict, by standard error. So some, in this case, 3 minus 0, standard error value I got from the regression, some value. I will show you what that standard error value is. I got some value. Based on that t value, we also get a p value. As long as that p is smaller than 0.05, I will reject null hypothesis. That means I will say that this is actually not true. Beta 1 is equal to 0. Beta 1 is not equal to 0. So I can believe on this value that I'm getting. So whether a variable is significant or not, that test is also done simultaneously while doing regression. That means whether the results that I'm seeing is valid outside the sample data that I'm playing with, that test is also done while doing a regression. So these are the very few basic concepts that we have to study before we can do the coding. The coding is very easy, and I will just show you. In the last class, I have shared this linear regression. Oh, I didn't share probably. Let me share the Python code quickly. Just 1 minute. I'm sharing this notebook to you guys. Give me 1 minute. Okay, I've shared it with you guys. It will reach in a minute or so. So once you have that, you can open it in Jupyter. Download it and open it in Jupyter. In the meantime, I'm launching Jupyter. So this is the notebook that I have that I will show now. So this is very easy basically. So this particular library is for plot. So matplot library is very like in R we have a ggplot library. Similarly here we have a matplot library. For any kind of plottings, this particular library comes in handy. NumPy is handy for doing any numerical analysis, and pandas is used to handle data, any kind of data handling, data reading, data cleaning. Pandas help. sklearn is for any kind of model building, like regression model or machine learning models that we are going to learn the next class, which is next module. For that, this sklearn comes in very handy. So I am first of all calling this, and then I am calling a Boston dataset basically. So under the datasets package, basically under the sklearn library, there is a sklearn has many things. So I'm not loading many things. I'm loading only datasets and then linear model and metrics. These three submodules I'm loading. I'm not loading all of them. So under the dataset submodule, there is a Boston dataset which is already there. So load Boston will load that Boston, and then I will convert that Boston. Boston is this dataset will be loaded in a form of a. So let me just show you what is happening here. So if I run this much, it's running now. This sign is black. It's running. Let it run. Yeah, so Boston will look like this. It's basically multiple arrays written as a dictionary. So the first array is your data set, and there is a target column also, and the feature names are given. So this is more of a dictionary. So I am converting it in a data one. So what I'm saying, so I'm saying data one pd.data frame. PD means pandas.data frame. So convert it to a pandas data frame, where there are two things. The data is equal to means the data frame will have some values in it. What are those values? The Boston's data array and Boston's target array. Boston's data array is basically a matrix, and Boston's target array is only one column. So basically, at the later point of time, we will predict this target using this matrix. And then what will be the column names? The column names is Boston's feature names plus target. So what are those feature names? The scream, ZN, Indus, CHAS, NOx, RN, age, dis, rad, tax, PT ratio, B, LStat. These are my basically the name of my X variables, and target is my Y variable. So I am just running it. Let me show you how the data looks like. The data ultimately looks like this. You see the last column is target, and these were my feature names. So Boston feature names. So these are my X variables, and these are my observations for all the X variables. What is my shape of the data? So if I want to know what is the shape of the data, data one dot shape, it is 506,14. That means there are 506 rows and 14 columns. Now, if you want to know what these things are, what the screen, ZN, blah, 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 this is a standard data set. So you can search Boston data set. It's a very standard data set that is available. The data set contains information collected by US Census Service concerning housing in the area of Boston, Mass. It is owned by blah, 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 and has been used extensively throughout the literature to benchmark algorithms. However, these comparisons are primarily done outside depth. Anyway, so what are the variable names? The target variable Okay, so the target variable is the price of the house. Basically, it is not written here. Yeah. So the last variable, so which I have written as price, is the median value of the home to be predicted. So that is the price. And rest, these are the X variables. So what are the cream means? Per capita crime rate by town. So wherever that particular place is. Zn is proportion of residential. Okay, so this is a town-wise data. Okay, so price is the median price of all the houses in that town, and these are the town-wise this data. So per capita crime rate, proportion of residential land zone for lots of 25,000 square feet. Indus means proportion of non-retail business areas per town. So ideally, as crime rate happens, the price should decrease. And proportional of residential land. The more is your residential land, the higher is the chances of price in that particular place. Let's say the index of accessibility of radial highways. The higher it is, the higher should be the price. Proportional of owner-occupied units built prior to 1940. As it increases, probably the price will go down. I do not know. It may be both ways. So like that. So different kinds of variables are taken. Now I am trying to predict the average median price, not the average price, the median price of home in that particular city. And then there are 506 cities are there. 506 cases means 506 cities are there. This data was originally published in hedonic prices and demand for clean air. So whether people actually look for clean air, and then they and that has some financial component in residential pricing is something that we are focusing on. So whether the city municipality, which relies on this kind of taxes, which is property tax and blah blah blah, should focus on keeping the air clean. It's a judgment call. So now, if that is the case, what I'm doing here, the first thing that I'm doing is creating a model. Now regression can be done using two kinds of this thing here, in the two kinds of packages in case of Python. One is this stat models package. Under the stat models package, there is something called SMF. So in SMF, this particular function basically uses very easy way of writing a model. So I am first importing that. Then I'm writing model is equal to smf.ols. OLS stands for ordinary least square. The method that I have shown of is called least square. So it is, I'm trying to find out the least square here, minimizing the square error, right? So that's why it is called ordinary least square method. So use the ordinary least square method, where target is your y variable. Tilde means this particular expression means target is equal to beta 0 plus beta 1 into P plus beta 2 into Zn plus beta 3 into Indus plus beta 4 into Chas plus beta 5 into Nox and so on. So that this expression is written by like this. It's a very common expression written in both R and Python like this. And data is equal to data 1. The data set that I will be using is data 1. So this particular line runs the regression and saves all the regression results in something called model. Now, results is basically the model fit, and then I print that result summary. So I will run this, and once I run this, I get this result. I'm not running, I've already ran it. So I get these results. So this result is also a very good view. You check that whether you know each and every value that is written here in this particular thing. So it is OLS, ran on 8th May when I actually was preparing this thing. There are 5,506 observations, 13 model variables are there. So you see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 variables in there. So that is 13. And this is basically residual n minus k minus 1. 506 minus 13 minus 1. This is basically the degrees of freedom of the residuals that is there. So that value is 492. Now, R square value that they calculated after doing this regression is 0.741. You see, adjusted R square is a penalized version. Adjusted R square will always be smaller than R square. It is 0.734. I'm not going into the values of F statistic because we do not use a lot these F values here in the case of regression. Although we use these values, the basic that we will basically discard the whole model if the probability of F statistics is not significant, if it is not smaller than 0.05. And then the log likelihood value is given here also. AIC, BIC, what the meaning of this I'm skipping as of now. It's not required in case of OLS. Now, what I'm getting here, I'm getting these are my coefficients. 36.45 minus 0, 0.464, 0.02. These are all my coefficient values that I'm getting. And then the standard error. Why this standard error required? Remember, I told you that T statistics will be calculated. And T statistics are calculated to check that whether these beta values that I got, the coefficient values that I got, whether they are significantly different from 0 or not in the population. So to do that, we basically divide this coefficient with the standard error. Why? Because the T statistic, as I wrote here, if you remember, it is beta 0 minus 0 by AC. That is beta 1 by AC. The estimate by standard error. So that's my T statistics, the estimate by standard error. So 36.45 by 5 comes to be 7.144. And so on. That's a 17.766 by 3.8 comes to be 4.7651, and so on. All the T values. These T values have been put in the T table, and they found out the P value. If the P value is higher than 0.05, for example, for this one, age, or for this one, Indus, these two are not significant. These two has no impact on the model. So what you will do, rather, that you will move these two values and then you will do your modeling. So you should rather drop Indus from here and age from here, and then you should run the model. Then you should run the model. Now you see all the P values are smaller than, higher than this thing. So this should be the model. So you should ensure as low number of P values here, which is as low insignificant variables in the model as possible, and the adjusted R square should be as high as possible. Now here I'm not doing any prediction. I'm only finding out the relationship between the variables and the model. Now to do any prediction, if you have done it in your logistic regression class, is that we divide it between training and testing. So to do that, I separating X and Y here. I'm creating separate variables X and Y, and then using sklearn to split it between X's training, X's testing, and Y's training, Y's training, testing. And the test size is 0.3. That means I'm taking 30% as my testing data and 70% as my training data. Based on that, I am just doing my splitting. So here I splitted the model. Here with the linear regression model. So linear model is under sklearn. If you remember, under sklearn, we have imported linear model. So this is a different library that I'm using. So linear model dot linear regression. This is the function name that the linear regression object I'm creating. And with that, I am doing regression with my training data only, X train and Y train. only training data. And I'm posting the coefficients. So these are the coefficients of 12 coefficients that I got from my testing data. So 13, because the first one is coefficient, which is the intercept. In actuality, if you have not got the age and in the significant here, for example, we dropped age and index from here, we should drop age and index from here as well. In actuality. Anyway, so this is the coefficient. Using this coefficient, I am now going to predict using my testing data. So here I'm predicting using my testing data, and here I'm calculating the RMSE. You see what I'm predicting? Predictions minus Y test. That means the Y values in the testing data. Then I'm squaring it up. Then I'm taking a mean, and then I am taking a square root of that. So whole RMSE is coming to me. Okay, so I have not run these predictions. So I have not run this regression either. This one. Yeah, so 4.523. So this is now if you have multiple models, when there are two objectives that you can choose. One objective is to find out the relationship between X and Y. When your objective is to find out the relationship between X and Y, so you are doing model comparison. If your objective is to find out X affects Y how, then you can compare with adjusted R square, or you can compare with F statistic. Whether one guy's F statistics is higher than other guy's F statistics. However, if your objective model comparison is prediction, whether your prediction is correct or not, here you will use the whole data. You will not break into training testing. Here you will break into training testing. Build your model on training. Don't bother about R square. Don't bother about adjusted R square. So we don't basically compare using adjusted R square. With this model, we do test predictions. And then compare based on the RMSE scores. Compare test versus prediction RMSE scores. So this is what we do. So we compare based on the RMSE scores only when our objective is to predict the Y variable for future. But when I'm trying to find out the relationship between X and Y, for example, we try to do that often in the context of, if I try to say that, okay, whether in Manrega has improved the, improve the condition of people in the country or not. Or let's say you have taken an intervention. You have used multiple interventions. You have done multiple digital marketing expenditures, and you want to know which one has impacted on sales in the past. You are not predicting future sales. You want to just predict the ROI of, or you want to the measure of the ROI of the various channels, marketing channels. Or let's say, in your case, let's say you wanted to, you are doing model validation. You wanted to check that whether the default rate of the people have reduced because of your campaign or not. Let's say you have decided to run a campaign that at the same time there were 2-3 interventions were done. Let's say for your credit people. One is that you have done a campaign that you should this campaign was a digital campaign, digital marketing kind of campaign, creating awareness that people should back their money on time, otherwise it impacts in their credit score and how it impacts in the long term. Some kind of campaign you have done, awareness campaign, let's say. Also, you have taken another initiative that there will be a call coming from your bank, reminding the people that they have some EMI due. Also, you have taken another initiative where mails will be sent, reminder mails will be sent. Now, some people got all these three, some people got two of them, some people got one of them, some people got nothing. You want to see that which one of these three initiatives that you have taken is actually working in increasing people's chance of or reducing people's probability of default. So when this is your objective, you are not trying to predict what will be somebody's so it's not a predictive analytics problem anymore. Since you are not trying to predict what will be the default rate in future. Rather, you want to measure that what is the effect of all this stuff on the default rate in the past. So you are more past focused than future focused. In such kind of a situation, you will do this model comparison using the whole data, not training testing separately. But if your focus was that, okay, a new customer comes in the group, and I know his income, I know his pattern, what is his default rate, probable default rate. In that case, you are a predictive problem. You are not past focused, you are future focused, and you will take the second particular thing, where you will break it into training testing, and you will focus on the model accuracy on the testing data, and you will not bother about the training data at all. So this is how the modeling works. That's why in one case I was asking you to focus on the adjusted R-square score 1735. In another case, when I am trying to predict the future, I was asking you how to calculate the RMS score. I'll stop here if you have any question. Any question from anybody?
So what would be the range for this RMS score? So it is 4.45 here. Is this a good score? This is a bad score?
There's no way to say that. There is absolutely no way to say that. So you should, so whether it is good score depends on what is the variance of this Y test. Okay, means you can try to say like this. For example, let's say if I, so this is basically your error that is left. Yeah, let's say I do a sum of this instead of me. I do a sum of this. This is basically the error that is left, right? And this is basically the error of this is the basically this total sum of square. Remember?
Yes, yes.
So then if I want to create a R-square score over for the test data, that will be something like this divided by this. Pretty good, I would say.
So since it is a test scenario, so basically your test data, so you can always go ahead and create the confusion matrix and see how many of those predictions have.
No, but it is a linear data. Now I cannot
Linear
create
data.
confusion matrix.
Okay.
I can create something like a pseudo R-square. This is a pseudo R-square that I created just now. Generally, people compare models using one RMSE versus another RMSE. But if you want to ask that whether I got one single RMSE score, tell me whether it is good or not. That I can only say like this. That now your model, I can predict your variance of your test data with a 78% variance can be explained. That's the accuracy level that I can say. Or some people also tell it like this, that let's say that. Please. I have a test data. You can say it like this, okay? That you can. There are other people who can do it like this. I got predictions, okay? If I got predictions, I can also find out this thing. Let's say if I got predictions other than RMSE, there's another way to judge this thing. If I got predictions, I can also have predictions plus minus 1.96 into the standard error of the Y. That is basically the interval predictions. This is basic. These values that I got in predictions are point estimates, right?
Yes.
I can also get interval estimates, and then I can check how many times Y test was in this interval. That can be said as a predictive accuracy. So if it is, you are expecting that 95% of times it will be inside by choosing 1.96. If it is lower than 95%, then your model is not doing good. If it is higher than 95%, your model is doing better. Even that can be one way of seeing the model accuracy. But generally, we compare. We say that one model versus another model instead of having one model. So the best way of saying it is that how my model is better is saying that what is the alternate that you have. If somebody asks you that how can I assume your model is good enough? The best answer, so there has to be a benchmark, and from that benchmark you can compare. When
So,
there is, yeah.
sorry, just want to add, I mean, so maybe RMSE we can for the benchmark, if we talk from model development perspective, so maybe we can compare the test and the trained data set, their RMSE, or maybe the out of time samples for RMSE. So I want to say that if the RMSE for the test set is higher than that of the training set, it is likely that I mean that we have overfit
The
data.
RMSE of test set is expected to be higher than the training set.
I mean, if it's much higher, I'm saying so.
If
I
it is
mean,
too higher, yes, there is an overfit problem.
yes. So maybe that benchmark we can say that okay, I mean, if we have a training set, so that from that we can compare our test set RMSE and maybe the out of time. So we see that okay,
No,
if the RMS.
Instead of that, why there is something called cross validation,
Yes.
k-fold cross validation, and etc. So you can directly do that rather than saying that comparing the overfitting. You can solve the overfitting in one go doing cross validation. So if you keep on changing your testing data and training data every time, and you have got different kind of beta values, and you take a mean of those beta values as your beta, then that will be a automatic solution to your cross overfitting problem.
Yes, but actually I was saying from that this RMSE perspective.
Yes, so RMSE can give you just an idea that whether overfitting is happening or not.
Yeah, and in general, I have, I mean, what I have read is, I mean, if lower the RMSE, better the model is.
Yes, that's true. That's true. That I just now have shown also. No, RMSE is what? RMSE is this value, this RSS score, or in the case of training data, this Y predictions minus Y test is the RMSE score. So the lower it is, the higher will be the R-square value.
Yes.
This R-square is on the testing data. This is not on the training data. This is testing data R-square that I just created. So that's all about the modeling. So what we have covered here is two basic things. I would ask you to try out this code on your own with this data set, and I will also suggest some solutions or some other problems that you can try out on your own. But I have just wanted to show the two purposes that are there but to do regression. One is to find out relationships, another is to predict. So we'll stop the session here today, and tomorrow we will have another session where this